Okay, thank you everyone for coming. This is enhanced support for value semantics in C++ 17. My name is Michael Park, perhaps better known as mPark. I'm a software engineer at Mesosphere, where we're trying to figure out what it would look like to have an operating system in the data center. Outside of work, I'm a member of the C++ Standards Committee, and I am also the author of the standard variant implementation in libc++. So this is the agenda that I have for us today. We're going to cover the basics of what it means to have value semantics for some of us who may not be familiar with the idea. We're going to cover 3 new library types that were introduced in C++ 17, which are optional, variant, and any in that order. Then I'll just go through a little summary of what I think, how they relate to each other and things like that. So value semantics. Before we get into value semantics, I want to first talk about distinction between values and objects. So it's important to note that when I say objects, I'm talking about objects in a sense of, in the C++ object model sense, as opposed to the object-oriented sense. So a value is an abstract entity, most typically representing a mathematical entity. So things like integers and matrices, right? We have, and they're abstract, and so they don't actually exist at a specific location or time. They just exist as an idea, as a concept. On the other hand, an object is a concrete entity, and they exist to represent a value. They are concrete in memory. They're made up of a sequence of bits and a type for us to figure out what those bits mean. And they come in and out of existence as time flows. And so naturally, values don't have an identity in memory, whereas concrete objects such as objects which are concrete have an address in memory, and we can identify them. And with this address is how we identify objects. So we actually have formal ways of describing this in C++ through value categories. So values, as I've defined it just now, is categorized as PR values, whereas objects are categorized as GL values. I'm not going to go into details as to how the value categories work and what the conditions are, but if you go to Nicole Mazuka's talk on Thursday, she's planning to talk about object models in detail, so she'll cover that there. So for us, let's just take a look at an example and figure out what I'm talking about. If you put your C++ hats back on the left we have 42, for which we can't take a value, which we can't take an address, right? Because it's a value. They don't have an address. On the other hand, on the right, we have int x equals 42, where we actually store that value in a concrete entity called an object, and we can actually take an address of that and refer to it. So what is value semantics? Value semantics as a whole is really a programming model in which we want to focus more on values and operate on values as opposed to objects. And in order to enable such a model, a systematic approach to deal with these pesky objects which come in and out of existence is necessary. So these are 2 strategies of managing objects that we really care about, at least for this talk. The first one is deep copy semantics, and the second is automatic lifetimes. So let's take vector as an example, since that's everyone's favorite type, right? When you copy a vector, you get an entirely separate copy, right? You get every one of your elements copied into a new vector, and if you modify the old vector, your new elements don't get affected. And it effectively severs the relationship between your new object and your old vector object, and that's what allows us to actually perform local reasoning with the state of the new vector that was created, because you don't care what happens to the old object once you copied it. Automatic lifetimes, also known as resource acquisition as initialization, is the technique where we achieve this by binding the lifetime of the array that's stored on the heap and the lifetime of the vector object itself on the stack, which is managed automatically. And so we can have the heap get managed by the lifetime of the stack, and we can bind those lifetimes together. So some benefits. Why do we even care? So first thing is that value semantics is the default mode in C++, right? It's been promoted for a long time, and we have a lot, as a community, we have a lot of experience with it. The fact that the compiler tries so hard to generate special member functions for you is indicative of the how badly C++ wants you to use value semantics. And we don't get a lot of defaults right in C++, but I think this one is the big one that we got right. And without value semantics, trying to read an academic paper, which typically is written in some form of mathematical notation, and transforming that to a program without value semantics is typically very difficult. And it's very difficult not because the algorithm is particularly complex, but you have so much more to worry about than the algorithm now, right? You have objects that you have to deal with in terms of like how to deal with their memory lifetimes and memory management and all that stuff. It's a lot of burden that isn't really actually related to the problem statement. And so what that means is getting value semantics and getting closer to mathematical notation actually facilitates us in reaping the benefits of the existing work that's happened in mathematics and computer science. The next thing is referential transparency. So we really get this from performing deep copy semantics, right? When we copy a vector, we get a new copy, and we can manage to not perform non-local reasoning all over your code base, and performing non-local reasoning is, I think, one of the hardest things to do in programming. And so deep copy semantics actually helps us increase opportunities for local reasoning in our programs. And we also avoid pesky issues like manual memory management, like we see in vector. And all three of the types that we'll see today bring value semantics to constructs that you already know about in the language today. So this brings us to optional. As I mentioned, optional was added to the standard library in C++ 17. The design is largely based on Boost optional, which was introduced in 2003 in Boost version 1.30. So the conceptual model for an optional is that it represents the notion of an optional object. Put another way, we can also say that it models a discriminated union of T and null op T. Null op T is the tag type that indicates that the optional does not hold a value. And so by discriminated union, I mean that it can hold either a T or a null op T, but not both. Another way I like to think about it is that this is actually a pointer to T wrapped up into a value type, right? So if we think about how this looks in, as illustrated by this diagram, I've declared some pointer P to some random type T. It points to nothing at the moment. And then we can create a new instance of T and assign it to P. And P points at T. And this is what we have. Now, if we move it over to optional, what we see is that when we declare an optional, now this thing is required to hold a value in place. So the optional needs to be at least as big as the largest, or in this case, it has to be at least big as T. So it's going to increase in size, namely as big as T, and then we're going to store the T inside the optional. Very clear on that? Okay. So here's a quick overview of the API. I've got optional string x here, which gets assigned the string hello. The first assert is going to use the operator, the implicit conversion to bool, to test for whether the optional holds a value or not. The second assert is using the operator star to perform unchecked access into the optional. So we're going to get the string out of the optional and test that we have the value that we expected. There's a second set of APIs. The default constructor for optional will default construct into the disengaged state, where disengaged means the optional does not hold a value. And we can use the has value function, which performs exactly the same operation as the implicit conversion to bool. And the value or function is used to provide a default value. If the optional happens to not have a value, then give me back this default value. One thing to note here is that the value or will actually copy or move the value out of the optional, right? So typically, if you go to access an element, a value inside an object, inside an optional, it's going to get you back a reference to that value, whereas value or will actually give you Not a reference, but a value. Okay. All right, and the value function is checked access. And so what that means is if the optional doesn't happen to actually store a value, then it's going to throw an exception. Specifically, it's going to throw the bad optional access exception. And as I mentioned, optional has value semantics as well as everything else we're going to talk about today. So if you assign x into y, then we're performing a deep copy assignment, and y holds a value now, and it's going to hold the same value as x. And the comparison will also be deep as well. And most importantly, automatic lifetime we talked about, and optional knows how to destruct the string properly. So I want to talk about some use cases where you can actually replace some existing practices with optional. And the 3 use cases that I want to cover are optional return values, function parameters, and data members. So first, let's talk about magic values. A magic value is a valid value of type t that is used to indicate the absence of value t. The absence of a value of type t. So that should sound weird and should be concerning. But we actually have this all over, we see this all over the place, right? We have, some of the examples are, we use -1, we use string endpause, we use an empty string. We also use the end iterator for some things that aren't necessarily range related. Sorry? Couldn't hear. NAN. Oh yes, right, yeah. Yeah, the comment was that the NAN value for double is also another special value. And we'll talk about that one later. So some of the problems. It's really easy to miss, and the reason why it's easy to miss is because it doesn't show up in the API, right? When you see a function that takes an int and returns an int, it's really difficult to tell that that int that you're getting back might not actually be an int, right? And if we're lucky, maybe it'll be in the documentation, but people are bad at writing and reading documentation, so I'm not all that hopeful about that. And secondly, we don't always have a value that we can steal, right? If the function f's return value, let's say, is an int, and all of the values of int are valid return result of that function, then which value do you steal? We don't always have this option. And we have an example of this, right? We have stir to L, which is a function that tries to convert a string into a long, and every value of long is a valid result of stir to L. And so it returns 0 for variations of the string 0 with spaces in it or whatever, as well as situations where you can't actually convert the string into a long. And yeah, it sets the value in error node to communicate the error, and the user is required to know about this. And this is even more subtle than knowing about the magic value and trying to check for it. OK, so this is an example. This is actually my favorite example of where this becomes a problem. So in this code, I have a fork call where we're going to fork the process that we're in. And as you probably know, we get back a PID, and we can test for the value of the PID to say, if it's 0, then I'm the child process, and if it's a positive number, then I'm the parent process. Now, fork can fail. So when fork fails, fork will return -1, as most Unix functions do. So we have -1, we check for 0, and we get into this else, and we think we're a parent, except we failed actually. But we're gonna proceed and try to kill the child process, which we failed. So PID is actually -1 in this case. So what happens when you call kill -1? Does anyone know? Kill yourself? No, that would be better. Kill all. If PID equals -1, then sig is sent to every process for which the calling process has permission to send signals, except for process 1 init, but see below. See below? What? I mean, this is what's below, right? We killed every process in our machine. So what happened? Well, we got a -1 back from fork, which meant that it failed. And then we propagated that value accidentally through the kill function, and the kill function said, oh, -1. Oh yeah, that means everything. So there's this completely different interpretation of -1 by what fork meant and what kill meant, right? It's kind of weird that kill would even take a -1 and say, rather than meaning nothing, it means everything. Okay. Let's see if I covered everything here. All right, so the accidental propagation of magic values is what's so dangerous here. So let's talk about optional return values. So here I have a parse function that's going to take a string view, C++17, fancy stuff. We're going to take the result type explicitly, and we're going to attempt to parse this string into a T, and that's what this function wants to do. So, okay, what happens if SV cannot parse the string into a T? The current solutions that at least I know about that I'll enumerate here is that one is obviously to throw an exception. Two, we could return a smart pointer or a dumb pointer, whatever, some pointer to T. We can return a pair of T comma bool, where the bool indicates whether the T is valid or not. We could return a bool and take a T-ref as the out parameter. And there are drawbacks to all of these approaches that I'll iterate through quickly. So throwing an exception doesn't really fit well if we don't really consider it an error, right? Let's say I want to try 3 different types of parses, and if it fails, it's not a big deal. I'll just move on to the next one. Getting through that through an exception is essentially using exceptions for control flow, and we frown upon that. Number 2, if we return a pointer, then immediately we lose value semantics, and we accidentally also pay for heap allocation. Pair T bool. This one's interesting. The T always has to be constructed, which means that oftentimes we end up adding default constructors to types that we didn't really want to. So that's one thing that we don't want. But the other thing is that the interpretation of what pair T bool means is actually ambiguous, right? So what I said is that pair T bool, if bool is set, then T is a valid value and we can use it. If bool is false, then it's an invalid value and we can't use it. Well, map insert returns a pair iterator bool. Well, what does it mean? Does it mean that when the bool is false, that the iterator is invalid, or the object that the iterator is pointing to is invalid? No. If the bool is false coming out of map insert, it just means that it wasn't the object that you tried to insert that I'm pointing at right now. So it's always a valid iterator, right? The interpretation of what pair T bool means is ambiguous. And the last one, this one's maybe the most obvious one. It still needs to be default constructed or constructed into something, and it leads to a very awkward API. So what happens if we introduce optional T as the return value? Well, we don't have exceptions. We maintain value semantics. By value semantics, I mean when we copy the whole value, and it manages lifetime. We don't get heap allocation because optional is not allowed to perform a heap allocation. T is only constructed if needed. And the intent is clear, and we get a cleaner API. And I say cleaner because I can't really call it a clean API, and the main reason for that is because trying to propagate the optional returns through a for loop, through lambdas, through different function calls is very manual and explicit, which oftentimes explicit is good, but verbosity is another concern. Optional function parameter. So if you have a function parameter that has that takes a type by value, so in this case we have some function f taking a light object by value, and we can transform that to take an optional light, and this will take in the existing optional, it would also take an instance of light, and it will just convert it, and within function f you can handle both logic. It's kind of nice. But what happens if we have some heavy object, and we're using const ref in the function parameter because we want to avoid copying because the thing is heavy? I've seen this code a lot, and I'm not sure that everyone understands the implication of it. So if we just transform the heavy there into optional heavy, where the const ref is on the outside, what happens if we pass an instance of heavy directly? Well, we're going to perform implicit conversion from heavy to optional heavy, and then we're going to bind to the temporary optional heavy that was constructed. And the heavy needs to, and the optional heavy actually needs to store the value internally, and so we're actually going to incur a copy, or at best a move, in this case. So this can actually be a copy, so watch out for that if you're making transformations. Optional data member. I have some person class here. First name, last name are mandatory, and some people don't have middle names. I don't have a middle name. And I've also been lying to you guys. My real name is not actually Michael. My real name is actually Chen Young, and that's my Korean name. That's my legal name. So I need to submit some forms to register for a new name, add a middle name or whatever. And once that process is, okay, fine, then I can actually get the name Michael as my middle name. Show you a few more things. Relational operators. We haven't talked about them much at all, but they're important because there are some subtleties here. So null op t, as I mentioned, is the tag type that represents the empty state of an optional, and it compares less than any t. And that's the so the null op t being less than anything makes optional by default total orderable, right? And so what that means is that you can toss optionals into a map, for example, and then operate on them as if they were t's, and have null op t as just another value. All the operators compare engagedness of the optional, then defer to corresponding operator t. So what this means is that you can't just define operator equal equal and operator less than and try to get away with it, because a lot of other types will actually do the inverse for you, right? Whereas optional t, if you perform operator greater than, then it's going to actually invoke operator greater than on your t. So if you're going to use optional t for some t, you have to define all the relational operators if you want to use them. And mixed comparisons are allowed. Optional t of optional u are allowed. You can compare also optional t to optional t to some value u. And the optional t and u comparison, the last one there that I showed, is actually really dangerous. And we'll see an example of that. The only benefit that I know of that comes from the optional t to u comparison is when you're doing heterogeneous lookup on associative containers. So if you have an optional t inside of a map, and you want to just look up by using a t without having to construct an optional t, then like we saw in the function parameter example, for instance, then you can use this comparison operator to actually perform that comparison. But it's a questionable use case, I think. So as I talked about relational operators being there in order to allow storing in containers. So yeah.
I have a question about the comparison. Mm-hmm. On one of your early slides, you were comparing optional string to char array. Is that safe?
Yes.
Isn't that optional GPU?
It is.
Okay.
Right, but there's a. The question was, I had an example where I had an optional string comparing to a const char star. And is that safe? Because that's clearly a optional t to u comparison. And the answer is that in that particular example, it is safe. And we'll go through an example where it's not safe. So storing in containers. So what I want to do here is vote on ice cream flavors. And this is the flavors that are available at my favorite ice cream shop. Assuming I live in San Francisco. They're pretty elaborate flavors. But some people don't like ice cream. Okay, so then they don't have a favorite ice cream flavor. I don't understand it, but fine. We'll make an optional ice cream flavor for them. And we want to take the votes, let's say that were stored in a vector of optional ice cream flavor, and we want to collate that into a map. And we can just iterate through the votes and insert it into a map and increment. And this works because you can compare optionals to each other, and map will just use that operator and it'll be fine. Okay, so this is an example where it's not safe. So optionalizing, by optionalizing, I'm talking about transforming a t into an optional t. And I thought I made up this word, but Merriam-Webster says it's actually a word, so okay. So this example, I have a car instance, and I have some max speed, and that's in kilometers per hour because I'm Canadian. It's going to have a get speed function, which will return the current speed in kilometers per hour. And we have some function that determines whether we can accelerate or not. And imagine this is some self-driving car that determines whether it can speed up or not, right? So we can say get speed less than max speed, trivially correct. Now, the speedometer might be broken. What do? We can't just stop all operations just because the speedometer is broken. Maybe we just don't speed up, right? And so let's say we make that be an optional and we return a null opt if the speedometer is non-functional. And let's say that we don't know about this use of can accelerate. Now we're going to invoke the behavior where we have optional t less than u. And because null opt compares less than everything, we'll say, yeah, you can accelerate. If your speedometer is broken, you can't accelerate. This is not good. So my recommendation here is that when you're making the transformation from t to optional t, either introduce an intermediate type which tries to delete the relational operators so that you can catch the instances of these and make sure that they're correct, or be really careful. But at least I wanted you to be aware of this problem so that you can look out for them if you run into them. And here's a summary of the delta from boost optional for those of you who may be really familiar with boost optional. Most of them are just incremental improvements. The one that I find is the most important is probably the forwarding constructor. Boost optional doesn't have a forwarding constructor, and what that means is my example of saying optional string x equals string literal doesn't work in boost. Whereas in C++17, that example will work because we'll perfect forward the string literal onto the string constructor. I'm not going to go through all of these, but this brings us to variant. And let's see, where am I? Okay. So the conceptual model for variant is that it's a type-safe union. Another way to look at it is that it's a discriminated union of the types that was given. And another way to look at it, that I like to look at it, is that it's an abstract base class wrapped up into a value type. And I'll show what I mean by illustration here. So again, we have some shape S, and we construct a circle and assign to it. And on the variant side, similar to optional, it's going to store the value in place. So the variant is going to be at least as big as the largest alternative. And then we're going to store the circle inside the variant. Quick overview of the API. I have variant in string, assigning a string literal. That's going to initialize the string alternative. We have a holds alternative function which tells you whether the variant is holding the type that you ask. The get function is a checked get function which gives you access into the value that the variant is holding. Variant default constructor. I don't want to get too deep into it, but variant default constructor is enabled if the first alternative is default constructible. So in this case, when I default construct the variant, we're going to initialize the int and default construct that to 0. We have the index function to check which alternative is currently active. Not particularly useful unless you're writing some kind of generic program. And a getIf function, which is another checked access, except it gives you a pointer failure as opposed to throwing an exception. So throwing an exception, the get function is a checked accessor that will throw an exception upon failure. And again, value semantics, destructor called correctly. Use cases. These are the three cases that I want to cover. We have union-like class, flat, closed class hierarchy, closed in quotes, and visitor pattern. So this is what a union-like class might look like. We're going to implement an animal hierarchy. It's a generic example so that you can relate to it perhaps easier. So we have cat, dog, horse, and we're going to create an animal hierarchy, a flat hierarchy. And we're going to use a union to store the values and use an enum to figure out, keep the discriminator. Then we can destroy the objects correctly, construct correctly, etc. And with that in place, we can implement this getSound function completely outside of the class definition, right? We can switch on the animal kind and then look into the values and do whatever we want with it to implement this getSound function. Now, this is missing a lot of code, right? This only supports construction and destruction. We don't support copy, we don't support move, we don't support accessors, assignment, visitation, etc. So after we add all of that, we would get value semantics. We're able to add new algorithms non-intrusively. What I mean by that is the animal class doesn't have to change, but it's error prone due to the manual pairing of enum and the value. We have to get the enum and the access into the value matched up perfectly, otherwise we have a bug. This is probably an example perhaps more familiar to people. We have an abstract base class called animal, and we have three classes that inherit from it, cat, dog, and horse. We're going to implement the virtual function getSound. So immediately, well, we lost value semantics because we can't be passing around inherent hierarchy like this without a pointer. We incur dynamic allocation when we have to manage the memory. Yeah, we can use unique pointer and shared pointer for that now, but it's still a memory you have to manage somehow. And dual citizenship is difficult, and by dual citizenship I just mean membership in multiple hierarchies, and that leads to multiple inheritance. And yeah, not a lot of people like multiple inheritance be included. And it's intrusive to add new algorithms. So to add a single algorithm, we have to actually go to every subclass of animal and add a separate function. When you're trying to reason about the getSound function, you might have to open up 15 separate files and jump across them to see, oh, is the getSound thing doing its thing, doing the correct thing? So it's grouped by type as opposed to algorithms, and sometimes we want them grouped by algorithms so that it's easier to see what's going on. So if you want to learn more about why classic polymorphism is not great, Louis has a talk on Thursday that you can go and check out. Visitor pattern. So visitor pattern existed for a long time. A lot of people have used it in the past. And this is kind of the ceremony of how to set it up, right? We forward declare the final classes. We declare the abstract visitor. Then all of the final classes define their accept functions where they pass along themselves so that we can figure out what the final type is. And then the usage of it, of using with getSound would look like this, where we define a getSound visitor, which inherits from the base visitor. And now we can't actually return the result directly because the visitor can't return results directly. So we have to have this intermediate result thing that we propagate the result out to. It works. It allows us to. So yeah, we got back the ability to add new algorithms non-intrusively, and that's more or less all we get with it. It's a lot of boilerplate, right? The ceremony was a lot, and then it's also inefficient because we have to do 2 jumps. So here's what it looks like with variant. We have cat, dog, horse, variant, cat, dog, horse. We're done. We implement the getSound function. We use the visit function, which allows us to write essentially the same code as what we were writing for visitors. So what did we just do? Well, we got back value semantics because variant has value semantics. It's going to store cat, dog, or horse fully within its object. You can add new algorithms non-intrusively, as we just saw. no manual pairing of the discriminator and the value. Dual citizenship is easy. If you want horse to be part of a transportation hierarchy, toss it in there, and it's just a horse. There's no association with either of the hierarchies. It just exists. One minus, maybe there's a code bloat. I haven't actually seen this in practice, but having 4 pluses seemed overly optimistic. All right, a few more things, and it's not all pretty, right? Because we're going to talk about value listed by exception now. So value listed by exception state happens if an exception is thrown during a type changing operation. So if I have a variant tu, and I'm in the t state, and I try to assign a u, and what we're going to do is destroy the t, try to construct the u in place. If that throws, well, we have nothing now. What do we do? So there were probably, I want to say probably around 2,000 emails sent around in the internal mailing list, in the standards committee, as well as a public forum that I started the fire on accidentally, to discuss what to do here. There were options like double buffering, always making a variant be emptyable, and what we got is a rarely empty variant. So if all of your types are no except movable, then you can't get into a value listed by exception state. How many people think this is true? How many people wish this was true? Oh, not a lot of people. Okay. So this is not true. Any variant can actually get into an value listed by exception state, and this is quite unfortunate, I think. So if we have some nasty struct that implements an implicit operator to int, we have a variant int float, which we think is innocent. Neither of them can throw during construction, except we can, right? We can have this nasty object when we try to in place, it's going to throw during an attempt to construct an int. Sad. Okay, well, so in what situations do we actually have to deal with this? Well, you already had an exception thrown, right? You would have had to catch some exception, and then you would have to proceed to ignore that exception and leave the variant in a value listed by exception state in order for it to have left the catch clause. So my recommendation is don't let value listed by exception state leave the catch clauses. So if it ever were to happen, keep it inside the catch clause, reset it to an empty, reset it to some dummy state or whatever, but don't let it propagate. And let's not be checking for value listed by exception everywhere, right? Not every function needs to check for value listed by exception at the top of its definition. And my argument for this is pretty simple. When you get a reference to an int in a function, right? Can you check whether that thing is uninitialized? No, there's not even a way to do that. But if you were to use it, it would be undefined behavior. So there are some cases where we don't even allow you to check for what the state of the object you got is. Another example that came up earlier was that nan is a magic value, and if you get a double inside every function that takes a double, do you check for nan? If you check for nan, if you're the type of person who checks for nan in every function, all right, yeah, go for it. Check for value listed by exception everywhere. But if you're the type of person like me who kind of trust others and assume that doubles probably aren't going to be nans all over the place, then we really don't need to be checking for value listed by exception all over the place for variant either. Let's cover a few more things. Monostate is similar to boost blank, if you're familiar with that. As a first type, it makes any variant default constructible, because variant will try to default construct the first type, and monostate is default constructible. So if you need your variant to be default constructible when you don't have anything else, when none of your types are default constructible, toss monostate in there and it'll become default constructible. It's a unit type to add an empty state to a variant, so it allows you to, so variant is supposed to be a discriminated union that holds exactly one value of the given types, right? And in this case, we want to actually explicitly add an empty state because we have some situation where it could be empty and it makes sense for our case. And the existence of monostate doesn't change any behavior for variant. So it's not going to say, oh, you have a monostate, so when I throw an exception, I'll try to see if I can construct that monostate instead to give you some more deterministic behavior. There's no special casing for monostate whatsoever. Monostate just exists outside of variant. Well, it happens to live in the variant header for not a great reason, I think, but it has no association with the variant class itself. The forwarding constructor, I think, is also interesting that I should tell you about. So in this case, we have some variant T0, T1, T2. I don't know what T0, T1, T2 are. They can be cons qualified. They can't be references, but they can be cons qualified, for example. So I have some foo, and I want to initialize it with the result of foo. I don't even know what the result of foo is. So which alternative is chosen? There must be some sequence of steps we take to figure out which alternative is chosen, right? So this is what we do. We have some ID class here, which just saves the type and not constructs anything. We're going to have this fun class, which is the has operator overloads for T0, T1, and T2. And we're going to attempt to call this function with the result of foo. And whatever comes out is the winner. So when you have variant T0, T1, T2, and you're wondering, how do I initialize, which one of these gets wins through what algorithm? It's overload resolution. So toss them all linearly, vertically in a overload resolution and figure out, well, that's a whole different set of steps you need to study, but at least it's leveraging one another. Okay, so let's take a concrete example. We have string, we have a bool. We try to initialize it with a string literal ABC. What's the result here? We're performing overload resolution with string and bool as candidates, and we're trying to invoke it with a const char array. Which one wins? Bool. Yep. So here's Eric's opinion about that. Variant string bool, and let's try the second alternative. Yeah, okay, I agree. Here's the delta from boost variant. The important parts here that I bolded are dynamic allocation during type changing operation and valueless by exception, which are essentially tied together, but I thought it'd be worth pointing out. Reference type support is not in the standard version, whereas boost supports reference types and some other ones. I don't think the other ones are all that important, actually. Excuse me. Okay, so shameless plug here. If you want to use variant and you don't have C++17, let's say you're back in C++11, mpark variant is a library that I've written to make variant more available for people. So this is C++17 variant, standard conforming, backported to C++11 and 14. So feel free to reach for that if you don't have access to C++17. Last type of the day, we have any. So the conceptual model for any is that it's a type-safe void star. I don't actually have really good use cases for any, but I'll show one. And another way to look at it is that it's a void star wrapped up into a value type. So again, another illustration. We have some pointer v to void, pointing at nothing. We can point at anything. And on the any side, we're going to actually have the same picture. So any doesn't hold the value in place because, well, how big should it be? It should be able to hold anything. So it actually holds a pointer. It's allowed to do small object optimization, but in general, it's going to create, it's going to perform dynamic allocation to be able to hold anything that it needs to. Okay, well, so what's the point then? Well, the point is that any keeps track of the type that it's actually storing. So if you pass around a void star and you cast it to whatever you need it to be, you have no idea whether that's defined behavior or not, and void star has no idea what it's pointing at. Whereas any will actually keep track of the type that it's holding, and when you go to access your value out of the any, if you get the wrong one, it'll at least give you an error. And as the other two types, we have value semantics. So if you wanted to pass around arbitrary data through binary boundaries and you wanted to have value semantics and not have to manage memory, then you could use any for that. So here's another overview of the API. We can have any x. Notice that this is no longer a string literal, because if it was a string literal, then any will decay that into a pointer and store the pointer instead. So I've got the string string literal. The s suffix, which constructs a temporary string out of a string literal, will allow us to actually store the instance of string inside of an any. Any has a has value function similar to optional, but it doesn't have an implicit conversion to bool. You can use any cast to get the value out of the any. In this case, we're getting the string, the reference to string, and then we can compare for the expected value. Any is default constructible. It will hold nothing. The type function will return type ID of void if it holds nothing. And if it's holding something, then it's going to return type info of the type that it's holding. And there are two forms of any cast. This form of any cast that I'm showing here is the pointer version. And it works similar to a dynamic cast. So in dynamic cast, if you give it a reference and you get a reference back, if it fails, throws an exception. If you give it a pointer, you get a pointer back. If that fails, you get a null pointer. So those semantics are similar, except any cast doesn't say, give me int pointer. It says int, and then you get an int pointer back. This is not how a dynamic cast behaves. You don't ask dynamic cast to give you an int, and it gives you an int star back, right? So that's a minor quirk, I think, that you should be aware of. Any cast is checked, as I mentioned. So in the y case, I'm not holding anything, trying to get an int out, can't do that. We'll throw in any bad any cast exception. Again, illustrating value semantics, where the string actually gets copied over deeply. And any doesn't provide any relational operators. And as always, automatic lifetime destroys the string correctly. Yeah, use cases, I only have one. And I categorize it like this. If and when a template can't work, and you can't use a variant. So what do I mean by that? Where could you not use a template? Getting through the virtual function, right? A virtual function can't be made template, and so you can't just pass arbitrary data through a virtual function. And let's say variant isn't enough because it's actually truly open to whatever type of you want to hold. So in this case, we have some consumer class and a virtual notify function, and we could use any to pass arbitrary data through the virtual function. This is the delta from boost any. Not much. Std any is mostly boost any kept intact. There weren't much that happened between those. And honestly, I think it's because not a lot of people use it and need it. So here are some minor differences that I found. So here's a summary of what we saw. These types that I introduced today, that we introduced in C++17 have value semantics, and I mentioned that these are the corresponding reference semantics that exist in the language today. And the number of possible states of each of these types look like that. So optional t, the number of states in which that optional t can be in is the number of states in which the t can be in plus the null opt state, so +1. The variant t's, if you have variant tu, the number of states that you can be in is the sum of the number of states in t and plus the number of states in u. So this is that described in C++17 fold expressions, because why not? And the number of states is infinite. It can literally hold anything, so there's no bound as to the number of states of an any. So this is my summary of how I think these three things are related. I'll point out again that an optional and any can be empty, whereas variant can't be empty, but it can be valueless by exception state. And this is the last thing I'll say, which is the empty state and the valueless by exception state is really different in that you don't, for example, when you visit a variant, if your variant has an empty state, you need to handle that empty state in your visitor. Whereas the valueless by exception state is not a state that you actually add. It doesn't appear as a case in your visitor because it's an invalid variant, right? As opposed to an empty state, which is actually a perfectly valid state that you actually are benefiting from. So that's everything that I had today. Oh, I have one more. Okay, so order of preference. When you're choosing which one of these do you think you should reach for, I think you should go for start from optional, see if that'll work. If it doesn't work, you have too many alternatives. Try to use a variant. If that fails, then use an any. So I think that should be the order of preference here. Okay, so that's everything I had. Any questions? I think we have 10 minutes left. Perfect. Do I just like conduct this myself? I guess? Okay.
On your own.
Sure.
So for a variant of TUT, the forwarding constructor, does it just...
Before?
Your constructor that was the forward constructor, does it simply, as you were trying to figure out with the algorithm, which to construct, which ID of T, is it the first index of T that you end up with?
No. So if you have duplicates, and you try to forward, the forward constructor is actually the same. So the question is, if you have duplicate types, for example, if you have variant TUT, and then you try to use the forward constructor, let's say you try to initialize the variant TUT with an instance of T, what happens? What happens is it doesn't compile. It doesn't just magically initialize the first one or anything like that.
Great, thank you.
All right, so I see that the standard vocabulary types, as opposed to boost, don't support references as a parameter. I know that, technically it will never store a reference since a reference is not a destructible object.
Yep.
But is the solution right now in the standard to use explicitly a reference wrapper or a similar type if we want reference semantics?
Yeah, so the question is, why is, or the vocabulary types, these I think refer to, qualify as vocabulary types, don't seem to support references directly, is the recommendation to use reference wrapper for when you need references. And the answer is yeah, but it's not good enough, at least in my opinion. But the answer is consistent throughout the library. Right? So this is one of the questions that I had when we first considered references in optional and variant. Why is it good enough for us to say, well, if you have a vector and you want references in there, then use reference wrapper. But for optional and variant, it's not enough. Right? So I think it should still be consistent. But the part where I say reference wrapper is not good enough is that if you, for example, have a function parameter, and you want to say optional reference wrapper int, right? Because reference wrapper deletes the R-value reference constructor, I can't actually pass temporary ints to that, right? This is not what you expect from a regular const tref signature, right? You should be able to pass R values to that as well. So I think, yes, that's the recommendation, but I don't think it's sufficient.
All right.
Does that answer your question?
Yeah.
Okay. Ben.
Hey, Michael.
Hi.
This might be an implementation question, but is there any size overhead of an optional T over a T?
Any
size overhead?
Any size overhead to the
is an
optional
T? How much bigger than a T is an optional T?
So from the implementations that I've seen, sorry. The question is, how much size overhead is there for an optional T compared to a T? From the implementations I've seen, it's generally just a bool, which with alignment might be a bit bigger than just a byte. So yeah, there is size overhead, and there is some ideas to figure out how to steal one of t's values so that we don't get that size overhead, but still provide optional like API. But yeah, optional as it stands today, it does have typically just a bool overhead.
So we're pushing the magic value problem is now the implementer's problem. Is that?
Essentially, except the user has to tell us which magic value they want us to use, right? So, because we can't just guess. It might be a valid value for them. So they have to tell us which one to use. But aside from that, I think the API could stay similar. Yeah. Hello.
Hi, Michael.
Hi.
I just wanted to say, as to like the optional ref thing,
Yep.
y'all should come to my talk on Thursday, because I will talk about that.
Okay. Cool. So there's a talk on Thursday. What's your name? Nicole. So there's a talk on Thursday, Nicole, that I mentioned. Yeah. So yeah, she'll be talking about optional object lifetimes and stuff like that, and optional references as well.
Yeah.
Cool.
Why
See.
it makes sense, and why the C++ community should support it, and how you have to think about references in order to get those kinds of semantics.
Why it makes sense, why the C++ community should support it, and what was the last part?
How you have to think about references in order to support
How you have to think about references in order to support it. Okay. See you Thursday. Hello.
Hi.
Hi.
My question is, you mentioned there's an invalid state to the
invalid state?
the empty state, so to say.
Of a variant or optional?
The variant.
Variant, okay, yeah. The
Well,
empty state or the valueless by exception state?
excuse me?
The empty state or the valueless by exception state?
Yes, the valueless
Okay, yeah.
exception state. What happens if you try to visit it while it's in that state?
Yeah, so if you try to visit a valueless by exception state, it will throw a bad variant access exception.
Okay, so it's another you had an exception to begin with, and then if you try to visit it.
Right. So yeah. So you got an exception that was thrown. You got into the valueless by exception state, and then we escape the catch clause, or maybe within the catch clause we try to visit it. If it's a value, and then it'll throw another exception out of that.
Okay. Thank you.
Yeah. Hello.
What is the state if regarding the double buffering problem for optional? Do we have the same problem there, or what happens if I assign a value and we throw an exception when we assign the new value?
Sorry, double buffering for optional? Did you say?
Yeah. So I mean, what's happening if my optional I assign a value and the assignment throws an exception?
Oh, I see, yeah. So this was actually part of my abstract that I didn't actually cover in the talk. The subtle difference between optional T and variant null opt T, variant null opt and T. If the optional is in the T state and we try to assign into it, we don't have this problem in optional because our alternatives are only T and null opt T. So whereas a variant would actually go into an empty state if we were storing a T and we try to assign a empty state and we throw, we're going to an empty valueless by exception state. An optional would actually stay in the T state. Yeah, Michael?
Okay, so since valueless by exception is clearly a state that's known to the object, is there a reason that a type like monostate type, but a valueless by exception type wasn't just decided to be held by the variant and used? I'm sure there was reasoning behind that. Do you know what the reasoning was? Like, why not construct the variant on failure with some type that represents a valueless type?
Right. So the question is, why doesn't the variant inherently have a valueless by exception state? And I think what happens if you do that is that a variant implicitly has an empty state.
Correct.
Right? And so it becomes a valid state of the variant, and it's embedded into the variant now, and yeah, it's a type that you have to cover when you visit it, for example.
Well, you have to cover the exception when you visit.
You have to
cover an exception when you visit?
You have to cover an exception when you visit.
Well, you have to. No, you can't. That is right. You can't write an overload that takes the exception.
Right.
That's my point, actually.
Okay. I think I'm out of time, and so we can talk offline, if that's okay?
Yes.
All right, great. Okay, cool. Thanks everyone for coming.